The got it problem for problem 2 is next. Again, these are not absolute value problems, so they will be straight lines, 1 and 2. Let's solve number 1 for y, so we can use y equals mx plus b, slope-intercept form. I'm going to take over the x, so I get 2y is less than or equal to negative x plus 4. I will divide by 2. Y is less than or equal to, and now remember there's a hidden 1 there, negative 1 over 2x plus 2. That one's solved for y and ready to be graphed. Number 2 is already ready to go, so I'll just copy it down. Y is greater than or equal to negative x minus 1. Let's graph the first equations. Go up 2, and then you need to travel down 1, right 2, down 1, right 2, down 1, right 2. Remember, you can also go up 1, left 2. Grab your ruler and connect. You are going to connect with a solid line on this one because it is or equal to. Remember, the line would be broken if it was just less than. This one will be shaded less than, which means if the line is falling, it will be shaded below. Remember, we're going to shade lightly on the first one. Let's go to the next equation. Go down 1 on your y-axis. Now your slope, negative 1 over 1. Down 1, right 1. Down 1, right 1. Down 1, right 1. Again, we have a solid line. Be careful to always look for that. I know our problems have solid lines, but they won't always. Connect and carry it through. Put arrows on it. And now this particular line is greater than. So I'm going to pretend my line is falling. Ready? Here it goes. It's falling. And I'm going to shade above that area. I like to use horizontal for one and vertical for the other, because then I know when the vertical and the horizontal cross, that's my final answer. So up here they're not both, but here they both have shading. Any point that I am currently coloring will be a true solution for x and y if you plug them in. Now you might wonder, what about the dots on the lines? What are those dot solutions? Since they're solid, yes, the answer is yes. The next problem will be applying this to a real-life situation. Your city's cultural center is sponsoring a concert to raise at least $30,000 for the city's youth services. Tickets are $20 for a balcony seat and $30 for an orchestra seat. If the center has 500 orchestra seats, how many of each type must be sold? Let's go ahead and talk about the money that they need to raise. We know that they need to raise $30,000 or more. So we're going to say that it has to be greater than or equal to 30,000. But we have two types of seats. We have balcony, let's call that X, and we have orchestra, let's call that Y. So $20 for every balcony and $30 for every orchestra has to be greater than or equal to 3,000. Let's take a moment and solve this for the letter Y. 30Y greater than or equal to negative 20x plus 30,000. Divide by 30. Y is greater than or equal to. When you reduce, this becomes negative 2 over 3 for 20 over 3. Plus 1,000. Alright, so we have our first limitation, and that limitation is actually the fact that it has to be greater than, because we want to make that much money or more. The other limitation that they told us about is that there's only 500 orchestra seats. So orchestra was Y, and we can't sell any more than 500. So we're going to say Y is less than or equal to 500. Both of these are ready to be graphed. We've dealt with all the restrictions. Now what you need to do is learn how to put it in on your calculator. Now down here I gave you all the different steps. You can see that I have the equations in, and look at the window how I changed it. I made the x minimum 0 and the x maximum 2,000. That's because I know it's going to be a pretty high answer. Okay, let's go ahead and take a look how to actually put it in your calculator though. You hit your y equals button. Now you might notice that on the paper I have these funny looking triangles. That's because the first equation up here had to be greater than. So when I put it in your calculator, I go over, I hit the left button until this is blinking, and I make it greater than, which just means I'm looking for it to be shaded above. Well, there's your triangle that looks like it's shaded above. Now I'll take my equation, and now this one has to be less than, so I'm going to hit enter until it's less than, and we've got 1,000. Let's change our window. 0, 2,000. We can skip by anything we want. We could skip by 100 if we want. Y minimum, what did I make it? 0. Maximum 1,200. We can skip by hundreds again. Now hit graph. That's the equation of the first line. That's the equation of the second line. All of this area that's double shaded, every single answer inside of here would fit the requirements of making $30,000 and selling less than 500 orchestra seats. Something that you'll have to become very familiar with in the next couple of lessons is figuring out where two lines intersect. Now you should already know this, you just set them equal to each other. But we're going to figure out what that point is right there. It's kind of like the edge, it's a vertice of where the double shading meets. So we're going to take our two different equations that we have, and we just replace y with 500 down here. Now if you had two equations and they were both set equal to y, you always just set the two different sides equal to each other. So to answer this question, where do they meet? We just say they meet where 500 is the same as negative 2/3 x plus 1,000. We'll solve for x, we have to take away 1,000, so when we subtract 1,000 on either side, we get negative 500 equals negative 2 over 3x. Multiply both sides by 3 to get rid of your fraction. So you get negative 1,500 equals negative 2x, and divide by negative 2. Negative 1,500 divided by 2 is 750. Now that is 4x. Okay? The y value, you can take this and you can plug it back in, but you better get 500 because that's what we said y is equal to. But just to prove to you that you could plug it in either equation, you do negative 2/3 times 750 plus 1,000, and you will get that 500 that we were setting it equal to. So if we're looking for an intersection point, the intersection point is 750, 500. What you need to do is be able to apply that to your problem up top. 750, remember, is the balcony seats. 500 is the orchestra seats. Okay? Moving on to the got it problem. A pizza parlor charges $1 for each vegetable topping and $2 for each meat topping. You want at least 5 toppings on your pizza. You have $10 to spend together on toppings. How many of each type can you get? When I scroll through this problem, I see that I have a maximum of $10. So what I'm going to do is I'm going to make a maximum of $10. So I'm going to make an equation that is less than or equal to 10 because I only can use 10. So whatever is on this side has to be smaller than or equal to 10. So let's find some other values that deal with money, okay? Because this is going to be my money equation. I see that I have $1 for every vegetable and $2 for every meat topping. I have my first inequality that I can graph. We need to figure out which one we want to be the x and y axis. We'll talk about that in a minute. Now another thing that it says is that you want at least 5 toppings. This is another total. Now if I want at least 5 toppings, that means that it needs to be greater than or equal to 5, because at least means you want that or more. So I say the veggies plus the meat. So I have my two equations. Notice this graph, you might want to write this down. This graph only includes the first quadrant because you can't order negative vegetables and you can't order negative meats. So we'll go ahead and solve each of these for a variable. I'm going to solve them each for v, since v is by themselves. That's going to make this axis the v-axis, and this axis the m-axis. You won't get it wrong either way, but I like to solve if v is by itself in both problems. That's how I like to solve. So in this equation, I'll take 2m to the other side. So that's v is less than or equal to negative 2m plus 10. We now know how to graph that because it looks like y equals mx plus b. This equation will solve for v again. V is greater than or equal to, in this equation, take the m over, negative m plus 5. So I have my two equations. I'm going to graph them over here. Now one thing to note in this problem, the reason it's an inequality, so let's write this down, it's an inequality because there are a range of answers. Okay? In other words, it's not saying that you want to be super exact, it's just giving you some limits, and then you have to find the range of the answers. So let's graph the first one. Let's go up 10, and then down 2 over 1, down 2 over 1, down 2 over 1. I'm going to do that until I meet both sets of axes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right here at the very top. How convenient. Down 2 over 1. When you connect these, think to yourself, should I be using a solid or a broken line? Hopefully you will decide that you need to use a solid line. So we connect using a solid line because it's equal to. And I'm only going to take it from one axis to the other to indicate, that I can't have negative slopes. The other equation starts at up 5, and it goes down 1 over 1. I will always encourage you to graph this until you come to the point where they indeed meet. In this case, they meet down here at the very bottom point. So I'll graph them. There they are. And now we have to think about our shading. We have to shade below the line that we graphed first. So we have to shade below this line. We have to shade above the line that we graphed second. So the only area that works is the area that's in between them, where they overlap. Now you might be wondering, well, what's my actual answer of this problem? Your answer is everything that's inside of here. Okay, so we will write all shaded area are possible solutions. If you write a couple of examples, one example of a solution might be, let's see, over 1, 2, 1, 2, up 1, 2, 3, 4, because 2, 4 is in the shaded area. That would be a viable solution. What would that mean? Well, since we graphed m comma v for x comma y, that would be 2 meats and 4 veggies. So I'm hoping that you can see that it doesn't matter if it's on the line or if it's inside. Anything on the line or shaded is an example of a solution. Now if I asked you for the boundaries, you should be able to tell me that the boundaries exist at 0, 10. See the corner way up here? That's a boundary. Another answer would be 0, 5. Again, you can see that that's another corner spot. And the other one would be 5, 0. And that's down here. Now are all three of these solutions? Absolutely, because they exist on the solid line. One more example of a solution could be over 1, 2, 3, up 1, 2, 3, because it's in the shaded area. And you can label those accordingly. So we have lots of examples of solutions. It's anything that's in the shaded area.